Alright, welcome back. We're going to go ahead and balance this last example from that previous slide. We've got aluminum bromide and chlorine gas producing aluminum chloride and bromine gas. And let's go ahead and do our tally. We've got 1 aluminum starting out, and 3 bromine and 2 chlorines. In the product, there's 1 aluminum and 3 chlorines and 2 bromines. This is again a single replacement reaction. So let's go ahead and see how we can balance it. I can start with either bromine or chlorine. Go ahead and start with bromine. Again, I'm going to need to find the number both of these can get to, so I'm going to go for 6. I'm going to put a 2 in front over here so that there are 6 bromines. I could have started on this side, doesn't matter too much. I'm going to start where we started, so 2 times 3 for bromine, we've got 6 bromines, and unfortunately, it's not that 2 is going to affect the aluminum and the bromine. So let's update the aluminum. That makes that our thread. So let's stick with aluminum now and try and get that to work out. To balance aluminum, I'm going to come over here, put a 2 in front, and that makes aluminum so much better. However, it changes chlorine as well. 2 times 3, the chlorine's going to be 6. And that chlorine was the thing that changed that we weren't expecting to change, so I'm going to go ahead and stick with that. I'm going to pop a 3 in front here, and that makes that 6. And nothing unexpected changed on this one, because chlorine's in the diatomic molecule by itself, so it's not with another type of atom that got changed. So let's take a breath, check in. We got these are even. These are not even and these are even, so the only thing we need to fix is bromine. So I'm going to go find bromine in the product. I'm going to put a 3 there. 3 times 2 brings that to 6. So hopefully, maybe some of those got all of them, got 1 or 2, but hopefully having them to check here might be helpful to make sure we're getting some of those right reactions or right answers as we are practicing balancing. So something I wanted to kind of mention is there are a couple tricks that make things easier, and one of the tricks that can make things easier is that if you see something written in parentheses on one side or the other of the equation arrow, it's probably one of those polyatomic ions that we mentioned right before our last test. And those are easier to count as a unit than to count the atoms in the polyatomic ion individually. And I'd recommend that you put them in the table as one thing rather than breaking it into the atoms in the part of it. So for example, in this problem here on the screen, we can see that there's this SO4 that's in parentheses. That's called sulfate. And if I look on the other side, I can see, oh, it's right there. So sulfate is 1 sulfur connected to 4 oxygens in such a way that it can pick up 2 extra electrons and make 2 bonds. And so it's a unit, it's a polyatomic ion that can work in that way. And so if you wanted to say that, you have potassium, K, and bromine, and aluminum, and sulfur, and oxygen, you can, and that'll work. It just makes it a little bit harder than saying I have potassium and bromine and aluminum and sulfate, and just treating this as a group. So let's go ahead and try this and kind of see how that works out. I'm going to pause for a minute and just write everything down if you would like to do the same. Alright, so the equation is written down on the paper and I'm ready to start balancing it. What I'd say is sometimes with the polyatomic ion thing, it can be helpful. When I write it, I'll actually put parentheses around the group that isn't polyatomic ion on the other side, just to help me identify when I do my tally how many I have of that group. So if we look, we've got 1 aluminum, 3 bromines, 2 potassiums, and then with the parentheses, it makes it a little bit easier to see I have 1 sulfate group. I have 1 sulfate group. What I find is when people don't put the parentheses, it's really tempting to say I have 4 of that group, but really I have 4 oxygens connected to sulfur, and that is a group, and I have 1 of that group. Coming to the side, there is 1 potassium, there is 1 bromine, there are 2 aluminums, and here's my group, and of that group I have 3 of that group. Cool, let's go ahead and start balancing. We can really start anywhere on this. So let's go ahead and start at the top. With aluminum, I'd like to make that match, so I'm going to put a 2 in front on this side. That causes that to become 2, and bromine to become 6. Bromine is the thread, so we're going to pull the thread. When I pull that thread, I put a 6 here in front to make bromine 6. Cool, but that changes potassium. So we're going to change potassium, makes that 6. And we're going to stick with potassium and try and balance it out. I'm going to come over here, I'm going to put a 3 in front, that brings that up to 6. And now I have 3 of this group. Well, what do you know? This was going to be my thread, my unintended change that we wanted to close out on, and so 3 times the sulfate means we have 3 of those, and we're balanced. So it's always nice when it comes so nicely full circle like that. Alright, that was the last of the balancing practice for today. The homework sheet does have some balancing on it, so you're going to be practicing that skill a lot. So let's go ahead and talk about kind of the new stuff for today. So the new stuff for today is bringing the mole back in. And so the deal is that number, I'm going to try and make this go away. No, that worked. The number that is in front, the coefficient, is the number of moles in a reaction. So it's the number of molecules, but it's also the number of moles. We know that in real life, most of the time when we're working with chemicals, we're not going to be able to get just 2 molecules or just 6 molecules of a type to mix together. We're going to have many, many molecules. And so that number, so in that example that is still on the screen, 2 moles of aluminum bromide and 6 moles of potassium bromide, that number means the number of moles that are needed for this reaction. And chemical equations are recipes. We're taking these 2 things together, and when we do that, we get something made, and the recipe is written in moles, so that's what those numbers are referring to. I should have mentioned that last example was a double replacement reaction. So let's see how this plays out. If we think about this equation here, this is the equation that we use, that has been used to power rockets for a long time. And so if we have 2 hydrogen gases, 2 moles of hydrogen gas, and 1 mole of oxygen gas, that'll make 2 moles of water. So to make water, we need 2 moles of hydrogen. We need twice as many hydrogen molecules as oxygen molecules. So kind of looking at it, we can start to sort of play around with this molar ratio thing. If I want to make 8 moles of water, if I want this to be 8, I'm going to need 8 moles of hydrogen, but I'm only going to need 4 moles of oxygen. So these balanced equations give us the ability to make a ratio. So go ahead and write this one down. The molar ratio is rewriting the relationship between 2 pieces of the balanced equation. So for example, that previously written equation, 2H2 plus O2 produces 2H2O. The molar ratio is just setting 2 parts of your overall balanced equation equal to each other. So 2 moles of H2 equals 1 mole of O2 is one possible ratio, right? And a lot of times we're just going to be asking you for 1 ratio. And so this equation has 3 possible ratios. So I wrote all 3 because I didn't want people to think, oh, it's only the first thing and the second thing equal to each other. No, any 2 can be set equal to each other. Remember, if we can set things equal to each other, we can write them like this, where they are written where one is over the other. I'm going to go ahead and move on. If you need to pause, always feel free. Yeah. What I want to mention is that we've used the mole before, and it's been a little while. We talked about how the mole is equal to 22.4 liters of gas, and about how the mole is equal to 6 times 10 to the 23rd molecules or atoms. We're not going to use the molecule Avogadro's number so much this semester, but we're going to use the molar mass quite a bit. We talked about molar mass in October when we introduced the mole. We also talked about it when we did percent composition right before finals, when y'all were making your own molecules. So this is something you've done before, so hopefully you'll remember it. But remember to find molar mass. You find your formula, you find the atomic mass of each element, you multiply the mass by how many of that type you have, and then you add all of those up. And then that'll give you your molar mass. And we can then use that to say that 1 mole is equal to the molar mass of that molecule in grams. So if it's helpful to remind yourself of those steps for calculating molar mass, please do. And then we're going to move on. So moving on, last thing I want to kind of mention here is how we can start to put all of this together. So how we can put all this together is we want a balanced chemical equation and some molar masses, and then we can actually use dimensional analysis from last semester to figure out how many reactants or products we can make or we will need. So with this, this is really what we're going to be talking about more next week, but I wanted to kind of preface it, and there are a couple problems on the homework for you to give a shot with it. So if we look at this equation is actually already balanced. We don't have to change the numbers because we have 2 hydrogens on the left and on the right. We have 1 sodium on the left and on the right. We have 1 chlorine on the left and the right. We have 1 oxygen on the left and the right. So it is balanced. All of the ratios are 1 to 1. So what's cool is if we know that we have 100 grams of hydrochloric acid, we want to figure out how many grams of table salt would be made from it. The cool thing is, if we use the molar mass of hydrochloric acid, and we know that that's equal to 1 mole of hydrochloric acid, I can use my balanced equation, where 1 mole of hydrochloric acid is equal to 1 mole of NaCl. These numbers are not always 1 to 1, but for this equation they are. And then I can use the molar mass of NaCl that we add up in grams, okay? I should have said that here in grams. And what's going to happen is the grams of HCl cancel out. And then the moles of HCl cancel out, the mole of NaCl cancels out, and we're left in grams of NaCl. And so this really beautiful, crazy, cool thing has happened where we can take a chemical reaction and actually figure out how much of something we can make given how much we are starting with. And so I'm going to go ahead and end it there because that's where we've been ending it in class. Go ahead and give those homework problems a shot, and we will check in on how they went next class. Thank you, as always, for all of your work and attention.